Okay, the ideal gas law. We can take those relationships in Boyle's law, Charles' law, and Avogadro's law and combine them into one gas law. And if I remember correctly, your book goes through how that's done. And if you're interested in that, you can look there. If you have questions, I'd be happy to talk to you about it. But most students really don't care how you would derive the ideal gas law. So we're going to kind of skip that. Yeah.
What is that symbol beside B?
This thing?
Yeah.
That is proportionality sign.
Okay.
It's a lot like an alpha. So that means that volume is proportional to 1 over the pressure, or volume is proportional to temperature. So if the volume goes up, the temperature goes up. So what we end up with when we combine all these things is this guy right here, sometimes affectionately called Pivnert. That's the ideal gas law, and that one's really important. PV equals nRT. So we've used P, V, N, and T before. We haven't seen that capital R. So the R is the ideal gas constant. So that's going to be the same because it's a constant, right? And the exact value of it depends on the units that you use. Just like, the length of my calculator, the number is going to depend on whether I measure that in inches or centimeters. So the one that we're going to use is right here. R is 0.08206 liter atmospheres per mole Kelvin. Those units seem messy, but that's what's needed to take into account the units of the other variables. That's something you should also memorize. 0.08206 liter atmospheres per mole Kelvin.
Is that what we're going to use?
We're going to use this one, yeah. There might be an occasional problem where we use a different one, but not very often. And the reason is that liters and atmospheres are convenient units for chemists to use. Other disciplines use the ideal gas law. They use it in physics, but they may prefer to measure their stuff with different units. And so they'll use a different value of the gas constant. Yeah.
So then whenever we're writing an equation and it gives us some information, do we automatically just substitute that number for R?
Yes, you will always use this for R. And the units on R tell us what units we have to use for these other variables. In order for this to all work out, the pressure has to be in atmosphere, the volume has to be in liters, N has to be in moles, and temperature has to be in Kelvin. Otherwise, the units don't work out. And so memorizing that can help you with the units on the other things. So this is showing how you can rearrange and end up with these other gas laws. And what I would like to show you is that you can memorize just the ideal gas law, and it's actually very easy to derive those simple gas laws from it. So P1 V1 equals N1 R T1. I didn't put a subscript on R because it's not going to change. If I divide this by P2 V2 on both sides, is it still an equality? Is it still equal? Yeah, because I did the same thing to both sides. But the ideal gas law says that this P2V2 is equal to N2RT2. And you want to start talking about C3PO and R2D2. N2RT2. That's a good imitation of R2D2. So everybody okay with that? So what I did is I took the ideal gas law with 1s and I divided it by the ideal gas law with 2s. So if I need, say, Avogadro's law and I forgot it on an exam, all I have to do is cross out everything that doesn't change. So let's say I'm doing an Avogadro's law problem where I have V1 and V2 and N1 and N2. The temperature is staying constant and the pressure is staying constant. Well, if the temperature is constant, that means that T1 is the same as T2. And anything divided by itself is 1, right? So those are going to go away. R is always R. R divided by R is 1. That goes away. And if the pressures are staying the same, then they go away too. So what do I have left? I've got V1 over V2 equals N1 over N2. You might be saying, well, that's not exactly what we had earlier. No, but I can rearrange it. That's the same as V1 over N1 equals V2 over N2. Avogadro's law. You can get any of those simple gas laws using this technique. I think that's easier than memorizing all of them. Let's do an example of a gas law problem. An 8.50 liter tire contains 0.552 moles of gas at a temperature of 305 Kelvin. What is the pressure in atmospheres and PSI of the gas in the tire? Well, we can tell that this is an ideal gas law problem because it's in the title of the example. Your exam problems aren't going to be titled like that, right? So maybe you look at this and you're like, I don't know what gas law this is. You can still use the make a table approach. So let's make a table. You know, our brains are tired. We're not thinking real clearly. We're just going to make a table, and hopefully it'll start to make some sense to us. So we write down the first number, 8.50 liters. Doesn't tell us what that quantity is, but the unit does. Liter is a unit of what? Volume. So that's the volume. Next number, 0.552 moles. What letter in the gas laws goes with moles? N. I know some of you want it to be M, but there is no M. Temperature of 305 Kelvin. Oh, nice. They gave it to us in Kelvin. We don't have to convert it. That's the temperature. They even said it was a temperature. We ran out of numbers. Oh, which equation doesn't have subscripts in it? The ideal gas law. PV equals nRT. So some people can read that problem and recognize there's nothing changing. This is a tire just sitting there. Nothing's changing. We just want to know something about it. That's going to be an ideal gas problem. If you don't recognize that, you can still make the table. What you're going to find out, though, is you have one of each of three variables, and they're going to ask you for the fourth. So we didn't really need the table, but it didn't hurt anything either. Right? We've got everything labeled now. It's okay.
The tire, when it's talking about the volume, that's just how much like gas can you fit in?
That's the internal volume of the tire. Yeah, you know, very inquisitive people will have questions like that. Well, is that the volume of the inside of the tire or the volume of the outside of the tire? And that's a good question. We're not trying to trick you with stuff like that in these problems. So you can assume that it's the volume of the gas in the tire. Okay, so what am I trying to find? I'm trying to find atmospheres and PSI. That would be the pressure. So I'm going to rearrange this equation to solve for pressure. The volumes cancel out. So I've got pressure equals nRT over V. So I need to put these in. N is 0.552 moles. What's R? 0.08206. And you know, if you just use that a few times, you'll remember it. Liter atmospheres per mole.
0.00.
Nope, 0.0. Yeah, that's a problem when you get the wrong number of zeros in there. And the volume, oh, I forgot the temperature. 305 K, extend this line. Volume is 8.50 liters.
Now, will those units with the R cancel out, so we don't have to leave it there?
Right, these units are going to cancel out, and that's what we want to happen. If they gave us the volume in milliliters, we'd have a problem when we need to do a unit conversion. So I plugged everything in with its units, and now I check the units before I do the math. So I see that there's moles canceling moles, and liters canceling liters, and Kelvin canceling Kelvin. I'm left with atmospheres, a unit of pressure, so that's a good thing. So now I can do the math. 0.552 times 0.08206 times 305 divided by 8.50. And three significant figures, 1.6254 atmospheres. I didn't round it there because I still have something else I have to calculate. But one of the answers is 1.63 atmospheres. That's one answer. Any questions about that? How do I get PSI from atmospheres?
The atmospheres times the PSI, which is 14.69 PSI per atmosphere.
Yeah, what he
I
said.
looked that up, I'm not that smart.
That's okay. So I need to do a pressure unit conversion. And from the questions I'm getting from people about their labs, I know that some of you are still not really grasping this idea of dimensional analysis where the units direct things. Okay? It really does make everything simpler if you do it this way. So I have atmospheres, I want PSI. So PSI goes in the top, atmospheres go in the bottom. Then I don't have to think about, am I supposed to multiply by 14.69 or divide? The units tell me. This is a conversion factor that you do not have to memorize. But it's 14.69 PSI, is equal to 1 atmosphere. That's not an exact conversion. The atmospheres cancel out, and I'm going to get PSI. So I'm going to take my 1.6254 times the 14.69. Now, this is a final answer. How many significant figures should it have? 3. Because this one only had 3. This has got 4, so it's not going to limit anything, but it's...
So would it have been okay if you used 14.7?
It would have been okay, yeah. I like 14.69 better. 23.9 PSI. So the pressure inside that tire is 23.9 PSI. You probably need to add some pressure to that. If it's a car tire, they usually are a little higher than 23. More like 35, a lot of them. Bike tires, 60 to 90. Put too much pressure in it, you'll blow it up. I blew up a wheelbarrow tire. That was exciting. Yeah, just about gave me a heart attack. Sounded like a gun going off.
Well, some people put it up where you get better gas mileage, like during the summer.
Yeah, some people do that. It's not a good idea.
But then the heat, especially here, already pumps it up.
The heat does pump it up some. It's not a huge difference because in terms of Kelvin temperature, going from 40 degrees Fahrenheit up to 105 degrees Fahrenheit is really not that big of a change, even though it looks that big in Celsius.
Some of the sports cars have nitrogen-filled tires, it's not that much difference.
Right. I have nitrogen-filled tires, but I don't have a racing van. It's just a football, basketball, baseball mom van.
Souped up there.
It's all souped up. Yeah, it's stashed with stale French fries and wrappers and extra
Where do
sweatshirts.
you get nitrogen at?
Actually, most tire places can fill your tires with nitrogen. I can't remember the exact reason why that's better. I think it has to do with nitrogen being less reactive than air, and so that your tires on the inside at least are not exposed to oxygen, which is pretty corrosive. Not that I know of. I think that nitrogen and air would behave much the same.
Isn't there nitrogen in our air?
There is nitrogen in the air. There's actually a lot of nitrogen in the air.
70%.
Something like that, yeah. It's a lot. Okay, let's do another one. What volume does 0.556 moles of gas occupy at a pressure of 715 millimeters of mercury and a temperature of 58 degrees Celsius? Okay, so now I'm going to pretend that I've gotten the hang of this now, and I recognize I don't need to make a table. There's one amount of moles, there's one pressure, and there's one temperature. I don't have changing stuff. So I am going to have to pay attention to some units, but I'm just going to take these numbers down and write them and label them. So 0.556 moles, that's what N is equal to. 715 millimeters of mercury, that's going to be the pressure. And it says pressure, so that's helpful. And then the temperature is 58 degrees Celsius. And the degrees Celsius immediately sets off an alarm that says, Kelvin, Kelvin, change it to Kelvin. That's probably the single most common error that students make. They'll forget to change it to Kelvin and they get the answer wrong. Plus 273.15. 331.15 Kelvin. I'm going to pretend that I'm not so with it that I recognize I need to change the pressure. So I'm trying to find volume. So I'm going to need PV equals nRT. And I'm going to solve this for volume. So I'm going to divide by P on both sides. Volume is equal to nRT over P. So I'm going to come over here and plug in these numbers. N is 0.556 moles. R is 0.08206 liter atmospheres per mole Kelvin. My sense of humor is hanging by a thread. So, yeah, not a good day. It's better than yesterday so far, but potential for who knows what. 331.15 Kelvin. And I'm just going to put my pressure down here
Why aren't you changing it to ATM?
because I'm pretending to not quite have this mastered. That's why I'm not changing it to atmospheres. So I stuck that in there because I wasn't really thinking, pretending not to think. And then, again, check your units before you do the math. So moles cancel moles. That's good. Kelvin cancels Kelvin. Atmospheres and millimeters of mercury. That's not going to work. I need to convert that. So I'm going to go back up here. And I need atmospheres. I've got millimeters of mercury. This is one you should have memorized. 1 atmosphere is 760 millimeters of mercury. And that's exact. So 715 divided by 760. So I didn't leave myself any room up there. I'm just going to write it in down here. That's 0.940. Those are my 3 sig figs that I've got. And then I'm going to put 2 extra digits, atmospheres. Now the units work out. So you do have to be careful with the units. 0.556 times 0.08206 times 331.15 divided by 0.94079. I forgot to keep track of sig figs on my temperature. This is my final answer, so I can round this. I should have 3 significant figures, and I'm going to get 16.1 liters. Any questions?
Is TOR the same thing as MMHG?
Torr and millimeters of mercury are different names for exactly the same thing. So if you had torr, you'd use the same conversion, but it would be 1 atmosphere per 760 torr. Any other questions? Yes?
The middle number, how do we say that? Do you say like the number and it's like per liters of atmospheres divided by?
It's 0.08206 liter atmospheres per mole Kelvin. Yeah. And they could make up a unit for that, but that would make things more confusing. Because this way, we can see what other units we need in here to cancel that out. Any other questions?